Hi students, welcome to the video lectures on the heat transfer lab. So today we will conduct the experiment on the determination of a Stefan Boltzman constant. So the objective of this experiment is to determine the value of Stefan Boltzman constant for the radiation heat transfer. So what is this radiation heat transfer? So already we have studied in the theory classes conduction, convection and radiation, that is three modes of heat transfer. So let us repeat it. So heat transfer from a body with a high temperature to a body with a low temperature when the bodies are not in direct physical contact with each other. It is called as the thermal radiation. That means when the heat radiation takes place from a body with higher temperature to a body with lower temperature, when they are not in direct physical contact with each other or when they are separated in space, it is called as the thermal radiation or heat radiation. So unlike conduction, convection, heat transfer, this thermal radiation, it does not require any material medium. So it may transfer in vacuum also. It does not require any material medium. So for conduction heat transfer and convection heat transfer, it requires a material medium to transfer the heat. But here for radiation heat transfer, it does not require any material medium. So energy transfer by radiation, it consists of then electromagnetic waves. Through the electromagnetic waves, the energy can transfer, and the energy transfer takes place at the speed of light also. So this is the tabular column. So before that we are going to calculate the Stefan Boltzman constant here. That means already Stefan Boltzman constant value, that is sigma, is given by 5 into 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So now what do you mean by this Stefan Boltzmann law? The Stefan Boltzmann law states that the total radiant heat power emitted from the surface is directly proportional to the fourth power of its absolute temperature. That is, Q is directly proportional to A into T to the power 4. If I remove this proportionality constant, where Q is equal to sigma into A into T to the power 4, where sigma is nothing but the Stefan Boltzmann constant. That's value is already given standard, that is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So that value we are going to calculate here by using the experimental method. So this is the tabular column. So this is the thermocouple readings. We are going to note down, that is T1, T2 and T3. These temperatures, it reads the surface temperature or the hemispherical surface temperature, where T4, it indicates the temperature, indicates the specimen temperature, where T5 indicates the heater temperature. So next, while conducting the experiment, we are going to note down the variation of temperature of the specimen with respect to time. That means for every 30 seconds we are going to note down the temperature of the copper specimen which we are using here, and that we are going to note down the temperatures at various timings. That is, for every 30 seconds we are going to note down the temperatures. So now let us conduct the experiment. In the today's class, we will conduct the experiment on the Stefan Boltzmann apparatus. Here our main aim is to calculate the Stefan Boltzmann constant by using this apparatus. So this is the stainless steel water tank. So where water is heated with the help of heater, and that heated water, we are going to take this heated water. I will show you the sketch here. We are going to take this heated water in this stainless steel water jacket. So when this hot water enters into this stainless steel water jacket, so let us wait for some time till it reaches its steady state. Steady state means, so on the hemispherical ball here, 3 thermocouples are placed here, which reads the temperature T1, temperature T2 and temperature T3. So as the heated water we have taken here, so After some time we are noting down the temperature, that is T1 temperature, T2 temperature and T3 temperature. So all these temperatures should be very nearer to each other. That means T1 temperature should also read the same temperature, T2 this also it should read the same temperature, T3 it should also reach the same temperature. Same temperature means up to 0.5 degree, up to 1 degree it may vary. That means all this T1, T2, T3 temperature should be nearer to each other. Then we will tell that it has reached its steady state. So when it has reached its steady state, that is hemispherical copper ball, then we are going to insert the hilum rod into this hemispherical ball. So I will show you this hemispherical, this is the hilum rod. You can see here. So this is the copper specimen. So the diameter of this copper specimen is 20 mm in diameter, and the thickness of this copper specimen is 0.8 mm thick. So now we are going to insert this hilum rod at the bottom. Some provision is made. So I am going to insert this hilum rod into this hemispherical ball. So this is here open space. So when I will insert this hilum rod into this copper specimen, so initially this copper specimen it is at now atmospheric temperature only. When I will insert this copper specimen into this hemispherical ball, the temperature of this copper specimen it starts to increase because it receives the heat from this copper ball. That means heat exchange takes place from this copper ball to this copper specimen. That means radiation heat transfer takes place. Already we know that heat always flows from high temperature medium to the low temperature medium. So initially this copper specimen is at atmospheric temperature only, which is at low temperature. So this hemispherical ball it is at higher temperature. So when I will insert this hilum rod into this hemispherical ball, that means heat transfer takes place from this hemispherical ball to this copper specimen, and the temperature of this copper specimen it starts to increase. So for every 30 seconds we are going to note down the temperature of this copper specimen. As the temperature of this specimen it starts to increase, we are noting down for every 30 seconds. So up to what level we are going to note down the temperatures? So when the temperature of this specimen for every 30 seconds, when we are going to get the same repeatedly the same temperatures, at that point we are going to stop taking the readings. So this completes the experiment. So now I have explained all the conduction part now. So now this you can see here this temperature T5 it reads the temperature of this water. Now initially the temperature of the water is at 34.6 degree. So now I will start the switch, and we will allow the water to reach the temperature up to its boiling point temperature of water, that is nearly up to 90 degrees centigrade. We will heat the water in this stainless steel water jacket, and where this T5 it reaches the temperature of the heater temperature, that means water temperature. So when it reaches 90 degrees centigrade, I am going to open this valve and I am going to allow the water to enter into this water jacket. So now we will allow the water to heat up to its 90 degree centigrade. So when it reaches 90 degree centigrade, then we will conduct the experiment. Now the temperature of the water it has reached up to 101 degree centigrade. Now I will stop the switch, and now I will allow the water to flow over this hemisphere jacket. Now I will open the valve. I will open this valve and I will fill the water, entire this hemisphere jacket I will fill the water. So here you can see here one valve is provided. When the water overflows from here, then it is assumed that it is full of jacket. At that time I will stop this valve. See now the water is overflowing, that means the water jacket it is full of water. So now I will stop this valve. So now let me take the temperature T1 is 95.2, temperature T4 is around 95, temperature T3 temperature T3 is also 95.9, means all the temperatures are very nearer. So this temperature T3 is 96.1, temperature T2 is 95.1, so this is 95.1 also. So almost all the temperatures are reading the same readings. So now let me keep for T4. So this is the initial at 0 time. The temperature of this is 39.5. As soon as I insert this hilum rod into this, so let us start taking the readings. So now I will insert this hilum rod into this. So now I have inserted it. So it starts increasing the temperature. So I will start it. So initially it was 39.3. So now 30 seconds is over, 45 degrees centigrade. .1 क्या आवाज कर लो कब 49.4. So we will take down like this way some 5 to 6 readings and then we will stop it. That is for every 30 seconds we should note down the readings like this way, and then we have to substitute these values in the answers formulas, and then we should calculate the Stefan Boltzman constant. 51.6. So like this way we will go on taking the readings. So another 2 readings I will take and then we will stop it here. .7. So like this way we will take the readings. So now I will take the readings and we will plot it in the tabular column. So next in the tabular column we have noted all the readings. That is T1 temperature is 95.2. Before taking the readings, so we have noted down the temperatures. T1 it is 95.2, T2 it is around 95, T3 it is 95.5. That means all these temperatures around the hemisphere, all these temperatures are nearer to same. So we have assumed that it has reached its steady state and we have started conducting the experiments. So T4 temperature, that is, this is the temperature of the specimen before inserting into the, that is, hemisphere ball. So when I will insert this copper specimen which is at temperature 39.3, then it receives the heat from the hemispherical ball and the temperature of this copper specimen it starts to rise. So T5, this is the water temperature, so it has reached up to 100 degrees centigrade. At that time we have started conducting the experiment. See here, at time t equal to 0 seconds, means before inserting the copper specimen, the temperature it was 39.3. so when I inserted this copper specimen into that hemispherical ball, so we have noted down the temperatures for every 30 seconds. So 45 after 30 seconds, so after again 30 seconds So it is 48.1 temperature. Again after 30 seconds 49.4 degree. Again after 30 seconds, that is after 120 seconds, temperature is 51.6. Again after 30 seconds, that is after 150 seconds, 52.7. So up to here I think we have taken the readings. So next also we have taken these readings, but we have not shown in the video here. So for every 30 seconds we have noted down the temperatures like this way for every 30 seconds. So up to what level we will take the readings means, so when we will get the readings, same temperature readings, same temperature difference, there we are going to stop here. We are at 660 seconds to 66.9, again at after 30 seconds 66, 90 seconds 67.4, here it is 67.9, again it is here 68.4, means for repeatedly we are getting maximum only 0.5 degree difference. So we can stop here taking the readings and then we'll do the calculation part now. So calculations, so area of the disk, that is A1 is equals to pi upon 4 d square. So pi upon 4, so this is the disk is 20 mm diameter, it is copper specimen, we have converted it in meter. So this is 3.14 into 10 to the power minus 4 meter square. So mass of the disk, that is M, so already they have given this mass of the copper specimen, it is 5 gram it is, so we have converted it in kg, 5 into 10 to the power minus 3 kg. So specific heat of the disk material, that is copper specimen it is. So specific heat already it is given standard, it is 385 joules per kg Kelvin. So now let us calculate the temperature, average temperature of this hemispherical surface, that is it is indicated by T of HS. So it is T1 plus T2 plus T3 divided by 3. So T1 is 95.2 plus 95 plus 95.5 divided by 3. So my temperature of the hemispherical surface, it is around, average temperature is around 95.23 degrees centigrade, which is approximately equals to plus 273. We have converted it in Kelvin, it is 368.23 Kelvin. So this is my average temperature of the disk before insertion. Already I have told you this temperature T4, it is indicated nothing but TS is equals to 39.3 degrees centigrade plus 273, it is 312.3 Kelvin. So next, this is same reading we have taken here. So rate of temperature rise of the disk, that is dt, that is change in temperature divided by change in timing. So this rate of temperature rise of the disk, so this value will calculate it from the graph. So at the end I will show you how this value is calculated. So rate of energy absorption by the disk, so this is given by the formula m into Cp into disk dt by dt, where m is mass of the copper specimen, that is 5 into 10 to the power minus 3. Specific heat of the copper specimen is 385 joules per kg Kelvin. So this dt by dt value, this is 0.05 value, this is taken from the graph. So I will show you at the end of this slide how we have taken this 0.05 value. So my rate of energy absorption by the disk is 0.0962 value. So rate of radiation energy exchange between the disk and the enclosure, that is enclosure means hemispherical surface. So this is given by sigma into A1 into F12 in the bracket THS to the power 4 minus TS to the power 4. That means heat is transferring from this hemispherical surface to this temperature of the copper specimen which is inserted in the hemispherical dome, where F21 is equals to 1 value. This is standard because F21 is nothing but it is called as the shape factor, or it is also called as the view factor. This F12 indicates rate of radiation energy emitted from surface 1 to the surface 2 directly. So as the copper specimen is very small, so we have considered this value as 1 because of the small body enclosure. So next, equating rate of radiation energy exchange to the rate of energy absorption by the disk. We are equating both these equations, that is the rate of radiation energy exchange and rate of energy absorption by the disk. So this is the rate of radiation energy which exchanges between the hemispherical surface and this copper specimen, that will be equal to rate of energy absorption by the disk. So therefore this sigma is equals to m into Cp into dt divided by dt, that will be equals divided by A1 F12 THS to the power 4 minus TS to the power 4. So this value already we have calculated, that is 0.09625 divided by, where area of that copper specimen is given by pi upon 4 d square, that is 20 mm. D is, we have converted it in meter here. F12 is 1, already we have taken here 1, so I have not substituted here. So 368.23 Kelvin to the power 4 minus 312.3 Kelvin to the power 4. So if you simplify this, so my sigma value is 3.45 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Here I have not written unit here, so its unit is watt per meter square Kelvin to the power 4, but standard value is Stefan Boltzman constant. Standard value is sigma is equals to 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So somewhere this value is nearer to that. So this completes the experiment. Sorry, now again one sheet is there. This is how we have calculated the dt by dt value. So here on the y-axis we have plotted the temperature in degree centigrade, that is 38 degree, 40 degree, 42, 44, 46, 48, 50, 52. Like this way we have plotted the temperatures on the y-axis, and on the x-axis we have plotted the temperature, that is time dt, time t in seconds. So for every 30 seconds we have I have drawn here. For 30 seconds, 60 seconds, 90 seconds, 120 seconds, 150, 180, 210 seconds. So like this way up to 30 seconds I have drawn here on the x-axis. So for 0 time, the value of the temperature was of the copper specimen, it was 39.3, somewhere it is here. For 30 degree we have plotted here, it is 45.2, like that way. For 60 degree, the value of the temperature. For 90 degree, what is the value of the temperature of the copper specimen. For 120 degree, what is the value, we have plotted like this way. For 150 degree, so what is the temperature of the copper specimen, like this way we have plotted all the values. So for any 2 or 3 points we should draw a straight line. So for this point and this point I have drawn with a straight line, or you can draw any other 2 points also, no problem. So this and this line are in a straight line, I have drawn a straight line here, and like this way we should draw one vertical line in order to read the temperature dt of the specimen, and we should draw another one horizontal line where it should intersect. It should be in a right angle triangle, like this way. So this is the dt. So here on the x-axis, from here to here it is 30 seconds, from here to here again it is 30 seconds. So total dt value is 60 seconds. So if I will measure here from this point to this point, so this is total 3 degree centigrade, that is temperature, 3 degree temperature. So dt by dt is 3 divided by 60, value is 0.05 degrees centigrade per second. So that value only we have substituted in the values, dt by dt as 0.05.